the session of study of aldehydes, ketones and carboxylic acids. All these are part of organic compounds, and till now you happen to study about the hydrocarbons in the first year. Coming to second years, you have studied haloalkanes, haloarenes which involved halogen compounds, forwarded with alcohols, phenols and ethers. With all these basic parts, now we will study another set of organic compounds which are called as aldehydes, ketones and carboxylic acids. And whenever we do study of organic compounds, we are quite clear of the aspects that we have to study. First up, we have to study the nomenclature and structure, then preparation, followed by physical properties as to what are their properties, then followed by some reactions that take place, and finally the uses. So, we will start this part here with the nomenclature and structure of these three type of organic compounds. So, when we talk about these compounds now, first up we see the general formulas that are present for these compounds. You can see some colorations that are being used there, where R indicates the alkyl group. Now, this alkyl group basically has examples of CH3 which is methyl. We also use C2H5 which is ethyl. Like this we can use any type of species which are there. Now, when we use these type of systems in this methyl, ethyl, propyl and all, here this constitutes the original base of the compound, where the carbon content of the system will determine the naming of the compounds, followed by the functional group that is present. So, first up, what is a functional group? Just as a revision, functional group is something that determines the properties of a particular compound. So, let us see those formulas which are there. The first up being aldehyde, RCHO. Second is ketone, which is RR-CO compound. The further functional groups here happen to be carboxylic acids, where RCOOH. That COOH part is the functional group for carboxylic acids. We have acyl halides, where X is the halogen, which can be fluorine, chlorine, bromine, iodine. All this are part of 17th group, and then that X is been attached to carbonyl group, which is CO. And acid anhydrides which have double carbonyl groups, that is 2 CO groups along with the oxygen in their cases. So, here the important part that we are going to see is that aldehydes will have the functional group of CHO, ketones will be represented like this, where on either sides we will have the alkyl groups moving around, whereas aldehydes have only on one side. This is further followed by carboxylic acids which are present, which is RCOOH. Now, in our study, these are the three groups that we are going to specifically concentrate on this chapter. Now, another important thing that we have to see in this cases is that the number of carbon atoms will determine the naming of these type of compounds. An important criteria that we see here is this CO group which is there. If I have to write the aldehyde in this way, this CO group which is there is called as carbonyl group which is present. Carbonyl, that is carbonyl, which carbon and oxygen. So, in all these cases, carbonyl becomes the central aspect of our study, where the hydrogen and R on one side determines it to be aldehyde, R and R dash determines it to be ketones, and R and OH determines these compounds to be acids in nature. So, having seen the basic general formula of these compounds, let us now slowly go through certain examples that are present in these cases. Whenever we go for naming, there are two aspects that we come across. One thing is the common naming that is associated with these compounds, and the other one is the IUPAC naming that comes across this. Now, the question is why there is a need for a common name as well as IUPAC name. Common names because earlier all these compounds were found out individually and they went on naming it, but later on they realized that too many organic compounds are there, and that is where IUPAC came into play and a proper structure was identified. The first compound that you see here, vanillin, is nothing but from the vanillin seeds that we get. Salicylaldehyde, you get it in many pharmaceutical products. Cinnamaldehyde, you get this in cinnamon, one type of cardamom which we see. So here we see that a common functional group in this is the CHO, which is aldehyde. Along with that, we also see other functional groups. For example, in vanillin, along with CHO, we are seeing OCH3, which is nothing but ethers, OR. OH, which is nothing but phenolic OH group. In salicylaldehyde also, we have aldehyde as well as phenolic OH group, whereas in cinnamaldehyde, we have an double bonded compound and then CHO. Similarly, acetaldehyde, benzaldehyde, and then finally, the compound that we have, beta-bromo-butyryldehyde. Now, the question is, what do we mean by this beta system? Beta indicates that whenever we have compounds of a particular major functional group which is present, the major functional group here is aldehyde. This can be known by the priority series that we have determined in the first year. Bromine in priority comes after aldehydes. So, considering a major functional group, the carbon atom beside it is named as alpha. The one beside that is named as beta, then as gamma. So, this was the common nomenclature which was employed, where this can be named as a beta bromo because the bromine is attached to beta carbon. So, beta bromo butyryldehyde because but indicates 4 carbon. So, the presence of 4 carbons here gives us the name but, and aldehyde is the naming that has been formed in common names. So, if these are some common names of aldehydes, let us see some common names for ketones also, where some of the compounds that are shown: acetone. Acetone is actually used in nail polish remover, girls must be knowing this well. Acetophenone, which is again an organic compound considering the benzene ring presence. Propiophenone, phenone for benzene ring. Prop word because after the benzene ring you have 3 carbon atoms, and then benzophenone, that is because 2 benzene rings are attached to the central carbonyl group, the ketonic group which is present. So, all these common names do not have any basis as such. They were just named because they were found out one by one in the early centuries, and the people went on naming those compounds. But once they realized that there are large number of compounds present, then came the presence of IUPAC naming which was present. So, in this IUPAC naming, the very first compound that we have there is been named as ethanol, and this example you also happen to see in common names where it was named as acetaldehyde. So, this is named as acetaldehyde, this is a common name. This is named as ethanol by IUPAC because 2 carbons indicates eth. 1 carbon meth, eth, prop, but, pent, hex, hept, oct, non, dec. Now, this nomenclature you have seen in the first year. So, considering presence of 2 carbons here, this has to be named as eth, and the functional group available is CHO. CHO functional groups are nothing but aldehydes, therefore, the name of this compound happens to be ethanol. So, al is the suffix for aldehydes, whereas prefix is generally we use it as formyl, but generally all these aldehydes come under suffix system. Second example, 4-bromo-3-methyl heptanal. Analyze the entire compound, you will see that 7 carbon atoms are there in the straight chain. In those 7 carbon atoms, number 1 is given to CHO. Reason being, the carbonyl group which is there has the highest priority. Number 3, because in the order you have to go, number 3 is given to methyl, number 4 is given to bromo, and therefore we have this name 4-bromo-3-methyl heptanal. The third example that we have is the cyclic system. And we know very well that whenever cyclic systems are present, we name these compounds as cyclo. Now, in this case, as cyclo compounds, there are in total 5 carbons in the cyclic system which is there. So, now the question is, where do you number it as number 1? There are 2 people here who are acting as substituent, and definitely number 1 has to go for ketone because of the priority series. Number 2, 3, 4, 5. So, this can be named as 3-methyl, and now because it is a cyclic system, we have to go with the naming cyclopentanone, Now the suffix of ketones is -one. So remember that aldehydes will have -al as suffix, ketones will have -one as suffix, acids which we study further will have oic acid as suffix. So since this is a ketonic compound, the name is going to be 3-methyl cyclopentanone. Moving to the next example, cyclohexane carbaldehyde, because in that compound a 6-membered cyclic ring is there and the aldehyde which is there is not part of the cyclic ring. It is rather present outside it. So for this clearer understanding, let me take two different examples which are there. So when I take such an example, if this compound is considered, this will become cyclohexanone, because cyclic because it is round, hex because there are 6 carbons available here, and one because it is a ketone. Now this is not ketone, this is aldehyde, and it is not part of the ring, it is outside the ring, and therefore the name will be cyclohexane separately as carbaldehyde. If you write it as cyclohexanal, it means that the aldehyde is also part of ring. But please see here that the aldehyde is not part of the ring, therefore the name will be cyclohexane. This is the normal naming that we have, and then followed by carbaldehyde. This is how we take up the naming of the compounds which are there. Moving to the next example there, pent-2-enal. Simple one, please see the total number of carbons. You will find 5 carbons. Number 1 obviously has to be given to the aldehyde. At the second carbon, you are able to find a double bond, and therefore it is written as -ene, pent-2-enal. Now why is -ene not written in prefix? Because -ene doesn't has a prefix. There is only suffix available for enes and ines. The last example, 1-phenyl prop 1-one. Now generally what happens is, whenever we have benzene ring, we consider benzene ring as the parent, but here we are considering as a substituent because to name the other part may be difficult. Therefore that 3-carbon straight chain is considered as parent, and to that ketonic part benzene ring is been attached. So these are certain IUPAC names of some compounds. We have some more compounds here. 3-oxopentanal. Why did this name come up? Because when you see the compound, you are finding 2 functional groups. One is ketone, another one is aldehyde. So the moment you have more than one, now you start to offer the numbers according to priority, and aldehyde has the maximum priority. So you number it from one side, you will get 3 for the ketonic group, and the prefix of ketone is oxo, therefore 3-oxopentanal. Similarly, the next one, 2,4 dimethyl pentane 3-one, because the parent chain contains 5 carbon, therefore pent. At the second and fourth carbon there is CH3 group available, and at the third carbon there is the ketonic group which is there. 4-nitrobenzaldehyde, because the benzene ring with aldehyde compound along with the aldehyde can be called as benzaldehyde. This is the benzaldehyde compound, and to this, if at the 4th position if we introduce nitro, because here the numbering will be 1, 2, 3, 4, at the 4th position the availability of nitro indicates that it is 4-nitrobenzaldehyde. Similar to this, this can also have a common naming system where this can also be written as para-nitrobenzaldehyde. Now para-nitrobenzaldehyde, because we know that by common names the 2nd and 6th position are called as ortho, 3rd and 5th position are called as meta, and the 4th position is called as para. So either name it as para-nitrobenzaldehyde or 4-nitrobenzaldehyde. Seeing the next example there, we have a combination of aldehydes now. Now the question here is, what should be the parent chain that has to be considered? In this entire compound which is there, we are able to see in total around 3 aldehyde groups in this cases, and the moment I consider any particular system as a continuous chain, the problem that I get is one of these tends to lag behind. For example, if I consider 1, 2, 3, 4, 5. Now when I consider that 5, another aldehyde is left below. So therefore the best thing that is done is, only the alkyl systems are considered for numbering. Number 1, number 2, number 3. And what are the aldehyde groups that are present? There is one aldehyde group available to first carbon, aldehyde group available to second carbon, aldehyde group available to third carbon. So in these cases now, the best thing that can be named here is that prop, because it's a 3 carbon straight chain that we are considering, prop 1, 2, 3 tricarbaldehyde. Tri because we have to name all the 3 aldehyde groups which are there. So prop is the carbon system that is present here in the parent chain, which is number 3. So prop 1, 2, 3 tricarbaldehyde is the name of this compound. So this is how the naming of these type of aldehyde and ketonic compounds are considered. And now let us go to the next set of compounds which are available here. We now come to the study of acids which are there, and generally even the aldehydes or ketones can be classified under aliphatic and aromatic. Aliphatic indicates the straight chain compounds, whereas aromatic indicates the presence of benzene. So in the first place here now, we will study only the aliphatic acids, and you are able to see some compounds which have common names as well as IUPAC names. IUPAC naming is quite clear that if there is only one carbon atom present. Now this is the functional group for aldehyde, the carboxylic acid COOH. To this, the general form R is given. Now here R can be replaced to this general form. If I take in place of RH, if I can see that this is in total a 1 carbon system. So a 1 carbon system can be named as meth, and since this is a carboxylic acid, the name will be methanoic acid. Similarly, with increase of carbon atoms, we can name it as methanoic, ethanoic, propanoic and all. Common names do not have any pattern. So they just are named according to the way they are got, and you can see here methanoic acid. The second one is ethanoic acid, which has a common name of acetic acid. Third one is propanoic acid, which has 3 carbon system. The common name is propionoic acid. The fourth one is butyric acid, common name being butanoic. Similarly, this is how we are considering it. Now in the further parts that are there, we see that the naming has changed now a little bit. What has happened to the next carbon system that has been shown in the example that we shall discuss here? In this case, there is also branching involved in the naming of the compounds. So what has happened is, they have named this compound to be like this, that there are 2 CH3 groups which are attached to CH and COH. Now when I try to split this open, what I can see is the carbon here is attached to 2 methyl groups. This is how we can split it open. And then this carbon is attached to hydrogen followed by carboxylic acid. So be clear that whenever you write a structure, carbon should be tetravalent, oxygen should be divalent, hydrogen should be monovalent. So that factor has to be very clear with us, and that is how we can write these compounds. So now the question is, how do you name this? Naming here will be, start numbering from here, because we know very well priority, we have to give it to carboxylic acid. Obviously the next one, number 2, what about number 3 now? Should it be here or should it be here? It can be either place because both remain the same. So this can be number 3, and that is how for the second carbon there is a methyl group which is attached. So this can be named as 2-methyl, and the parent has 3 carbons, so therefore we can name it as 2-methyl propanoic acid. Propanoic acid because COH group is present, a 3 carbon parent chain, and to the second carbon there is methyl group which is present. So seeing the next example which is available for us, we have some dicarboxylic acids now. So what are dicarboxylic acids? Those which have 2 COOH groups in them, and common name again COOH, COH together we call it as oxalic acid. And what is the IUPAC name now? IUPAC name, once again, if you see the compound, there are in total 2 carbon atoms, so therefore the name eth stays on. Ethane dioic acid. Now the di word is there because in total we have 2 COOH group. So that is why the naming now, earlier if you see it was ethanoic acid for 1 COH group. Now if it is a 2 carbon system, we name it as ethane dioic acid because 2 COH are there. Similarly, propane dioic, butane dioic, pentane dioic. Common names, as usual, they will have their own set of nomenclatures. These are now some compounds which are aromatic acids. We have already seen that aromatic acids indicate the presence of benzene ring in their compounds, and this is one of the important acids that we tend to seek, which we call it as benzoic acid. So, generally when we want to study the basics or certain reactions of aromatic acids, this is one compound that we tend for majority of the reactions. So, benzoic acid, because the benzene ring is attached to the COOH group which is present. Similarly, we have some more examples there, phenylacetic acid, because 2 carbon system is there, CH2COOH, and there is one benzene ring which is taken as substituent. Phthalic acid is a dicarboxylic acid, but here it is aromatic in nature. The common name is phthalic acid, but then how do you have the IUPAC name of this compound? So, this is how the compound I tend to write, where COOH group which is present will have benzene as the parent here, because that is why I will write it as benzene hyphen 1, 2, because this has to be considered as the first carbon and second carbon. So, in these cases, these parts which are there can be considered as benzene 1, 2 dicarboxylic acids. Benzene, first and second carbon carboxylic acid, and because there are 2, we have to name it as di. Please remember that even if I write this structure COOH, COH, this is also benzene 1, 2 dicarboxylic acid. Please do not get confused. It is just that the position of OH groups are different. Here it is written here, whereas here it is written here, but 3-dimensionally it is just that they are present one beside the other. So, these are certain structures of the organic aromatic acids which are seen. So, having seen all the structures, now let us see another concept related to these compounds, which is nothing but the structure of the carbonyl group. Now, how is the structure of the carbonyl group? 3-dimensional view is shown to you, but if we have to study this compound pretty well, let us see how does it manufacture itself. So, in the carbonyl group, it is mainly the C double bond O which is of prime importance for us. To this C double bond O, carbon has to be tetravalent, we are pretty clear with that, and it depends on the compound which is there. If it is aldehyde, it is like this. Suppose if it is a ketone, then the CO at the center remains the same, whereas this becomes R and R dash. If it is carboxylic acid, the CO at the center once again is same, but this is R and OH. So, these are certain changes that we see, but how is the overall structure of this compound is important, where hydrogen and carbon have almost similar electronegativities. This was studied in chemical bonding chapter of first year. And what is R? R is also nothing but some carbon compound. If you consider CH3, it is methyl, C2H5, ethyl. So, whatever it is still a carbon compound, and therefore, the electronegativities will remain same. So, now the question comes between carbon and oxygen. Carbon and oxygen have different electronegativities, because if you see in the periodic table, carbon atomic number is 6, oxygen is 8. So, naturally what will happen is this will hold a partial positive charge, this will hold a partial negative charge. So, supposing if I break open this compound, then how it will be is, it will be CO, where the negative charge will be transferred there and positive charge will be completely transferred. The indication of delta indicates that it is partially present. Partially negative indicates that these electrons are attracted more towards oxygen. Similar aspect continues for other compounds also, because here the stabilization is also the same, where the electronegativity difference between carbon and oxygen determines it. The problem only comes that for this carbon, where it has been attached to 2 different oxygen atoms. So, how do we see this part here? In this case, this bond is a sigma bond, the single bonded system. This is also sigma bond. Whenever 2 bonds are there, the first bond is sigma, second bond is pi. This was very well known to us in the chemical bonding chapter. So, the pi bond is the weak bond, and that weak bond is the one which fluctuates, or it is been attracted towards oxygen. So, in total you can tell that the carbonyl carbon has 1, 2, 3 sigma bonds and 1 pi bond which is present. Similar cases with these two also. But as I told you, the difference of charges, how does it work? That let us see in another picture here, where you will see that this carbonyl group C double bond O has a differentiation of charge where positive charge is concentrated towards the carbon of the carbonyl group, whereas negative charge is concentrated towards the oxygen of the carbonyl group. So what has happened to these carboxylic acid structures now? These carboxylic acid structures tend to show the separation of charges, because since these are acidic in nature, this RCOH very easily it can give out H plus. Giving out H plus here is difficult. Reason being, this is negative, this is positive. Can a positive stay with a positive? Like charges, do they attract or repel? They naturally repel each other. But if this is positive, another positive part cannot come and stay there, because the stability of the system will be disturbed. So this hydrogen cannot be positive, but this hydrogen can definitely be positive, because oxygen is electronegative and hydrogen is positive. So in this case, if you undertake a separation, RCOO minus and H plus goes away. So this RCOO minus, what it does is, it undergoes a stabilization where the negative charge which is there is fluctuating between these two carbons. So what has happened here is, earlier the negative charge was of this oxygen, now the negative charge has gone to another oxygen. So together how we show this compound is that, let me just show it here down, where COO, and I will show it as a dotted line with a negative charge. What does it indicate is, R and C are stabilized on their own. The negative charge on the oxygen is having resonating fractions between the two oxygen atoms. So there is a continuous resonance that is happening, and we know very well that double arrowed marks, one way we show it for reversible reaction, also for resonating structures we show this type of arrow marks. So this is how we can analyze the structure of the compound, and where is this useful is in the reaction. Because if this is positive, it means that in these cases nucleophiles can come and attack. Because what are nucleophiles? Nucleophiles are electron rich species. So to the positive part, nucleophile can go and attack. What about oxygen? Electrophiles can go and attack there. This is how we can understand how the chemical reaction can take place, and this will study in the further parts that are present. Similarly here, with this splitting, we can understand how strongly acidic a particular acid is, or whether it is a weak acid as such. So this is all about the nomenclature and the overall structure of the various carbonyl groups that we are going to study in this chapter. Thank you. Sai Ram.